split in the class, right? so maybe it's not.
Well, if you consider both,
then it gets complicated. Yeah.
Well, basically, we don't have enough data to make the decision right now because basically we have to calculate both scenario with proper data. So unfortunately, we don't have.
So you need life cycle assessment to do that, right?
Yeah.
So luckily, I've already done those calculations. I'll just skip through some of this stuff, but so just thinking about the goal and scope of doing this study, the policy questions that I was asking are there opportunities in the near to midterm to improve efficiency and environmental impact of infrastructure investments and use in this particular case? And then specifically, are there alternatives to shipping coal by rail that would improve both the cost and or the environmental impact? Just to complicate this just a little bit more, when I was looking at this, I was assuming that the power plant that you would build would be a pulverized coal plant. So that's a typical coal plant. That all the current plants in Alberta are pulverized coal. Most throughout the U.S. are coal as well. And so this is a typical technology, but there is a different technology that's sort of being put forward, which is a gasification system. So instead of just pulverizing the coal and putting it into a boiler system where you burn it, this is actually where you get it into small pieces and you actually react it with steam. And so it's more of a chemical reaction that you have that occurs. And that is a more efficient way to actually use the coal, and you can generate the electricity that way. And so as I started going through this, that was an option that I wanted to look at. And a typical gasifier is a Texaco, it's now a GE type gasification system, actually creates a coal slurry, so actually mixes the coal with water and injects it into this gasification system and reacts it to generate this synthesis gas that actually then you can use to generate your electricity. The problem with it is that the subbituminous coal has a high and variable water and ash content. And both of those are problematic when you use this type of gasifier because you've already got a bunch of water in the coal and then you add more water to it. And so you get to the point where, and because it's variable, operating this type of system is more difficult. And so you get these inefficiencies in the process when you use that type of coal in this type of gasifier. But this was the one that was sort of on the market. And so with the overall efficiency of the system, a typical pulverized coal plant would be about 34% efficient, 33 for this type of coal. And this system was down at 30%. So it didn't seem to me like you'd want to be doing this for this type of coal. The other type of gasifier that I looked at was this Lurgi dry ash. And so one of the benefits is that you actually put dry coal into the system so you don't have the moisture problem. And it operates at temperatures and pressures that are better for this particular type of coal because of the high ash content that's in there. So this system worked better, but this system is amenable to actually producing a synthesis gas that works well to be methanated using a nickel catalyst to actually create synthetic natural gas. So you can actually take coal and produce synthetic natural gas from it. And so this process, what the benefit of this process is that it's highly efficient, so it's 69% efficient one comparatively. And then if you actually put it through a combined cycle natural gas plant, you get higher efficiencies than a coal plant. So the coal plant's down at 34. The gas plant is 49% efficient. And so there was actually this added benefit of actually creating synthetic natural gas and using the natural gas in a combined cycle plant that is more efficient. Yep.
If you use a combined cycle plant, you have to be near the population, don't you? Or near a center that can use the heat, the waste heat?
Well, no. So the combined cycle is actually using two different types of turbine technology to actually generate electricity more efficiently. The combined heat and power system would be a different type of system that you could use. Okay. But the waste heat that comes off is important if you wanted to try and improve the efficiency of the system even further. And that's where, being in a remote location where there's not a lot of industrial processes that could use that waste heat versus an urban center might make a difference in terms of the calculations that you'd be looking at. So anyway, so this option looks like it might be another promising option. So I actually added that in. So now we have 4 options that you could generate the synthetic natural gas and burn it on site in a combined cycle unit to generate the electricity. Or you could actually, this would generate synthetic natural gas that's pipeline quality. So you could actually put it through the natural gas pipeline system network and generate the electricity using a combined cycle plant in Texas as well. So those are 2 additional options that you could look at. So the way that I calculated this, I looked at the capital investment that would be required as well as the operating and maintenance of those systems. So those 2 sort of typical cost calculations. The other thing I looked at was the social costs, so the safety, the human health, and the ecological impacts. And what I tried to do was actually monetize those and internalize the externalities associated with these things. So actually to put a dollar value on the air emissions that were coming from these plants. Just a slightly controversial area in terms of what value you actually place on that. But it was to attempt to try and see if you could actually internalize those costs and if that would influence the decision. So this is just some of the details of the model and what I was looking at, and conducted all the life cycle details. So you're actually looking at each process, inputs and outputs associated with each of these processes, but I'm just going to jump to the actual results. This was the plants, so I had to size the plants. I had to put specific environmental controls so that they would actually meet regulations in the jurisdiction where they were being operated. So sulfur control, NOx, particulate matter, all of that kind of thing. And the net output. So I had to take into account the difference in where the plant was located in terms of the losses on the transmission line, right? And the way that I compensated for those line losses is I said I had to generate more electricity in Wyoming to end up with the same amount of electricity in Texas, right? So there was additional amounts of coal being burned to generate that additional electricity, which means that the environmental emissions associated with that are higher than if I was shipping it by rail. But for the rail system, I had to take into account the energy that was required to actually operate the rail system. This was an example of how I used that EIOLCA tool, the Economic Input-Output Lifecycle Assessment tool, was I got the transmission line project costs from a consultant that built transmission lines. So the total cost, this is in millions of dollars, so it's almost $1 billion. And then I got it broken down by where the expenditures occurred. So how much aluminum was required, the electronic components, the steel, the land purchases that were required, so all the details associated with where you would actually spend the money to build this transmission line. And then for each of those, I could run them through the EIOLCA tool and get what the emissions associated with constructing that transmission line were. I did that for all the components. This is just an example. This was the line loss issue that we talked about. And so this is what the base case annualized cost looked like. So I took the capital cost, the operating cost, I annualized it all, as well as the social costs that I was talking about. So these are the total cost results, and it's millions of dollars per year. So the total is that the rail system is the most expensive, and this is assuming that no infrastructure exists. Okay, so it's a simplifying assumption to start the calculation. We've already talked about the fact that existing rail system is there, but it's not clear you can make use of it. So as a base case, I assume that no infrastructure exists for either of those. If you had to build it, the rail system is more expensive than the transmission system to build, right? So it's the most expensive. The cheapest option is to build a coal by wire. And then if you're going to build that gasification system to build synthetic natural gas, the other two are sort of in between those two. You can also see that it's dominated by the capital costs, that once you actually build these systems, to operate them is relatively small. The rail system is the most costly to operate though as well. So it's the most costly to build and operate. The fuel costs are sort of comparable, but the most expensive is the rail, and that's because you're using diesel in a diesel electric locomotive. And that diesel is much more costly than the coal you would use for the transmission system, so that could be a little bit of a difference. And then these are the externalities, and you can see they're the smallest contribution, and this is all the social impacts, all of the emission impacts associated with the air quality impacts and ecosystem impacts. And so this is from a literature that takes studies about the asthma attacks and the deaths that occur associated with this air quality issue. It also takes into account the rail deaths, and it's pretty significant. There's about 1,000 rail deaths per year in the U.S., and a good chunk of those are from rail transport. And so it's grade crossings and all of those kind of things that are included, and so that's included in the externalities as well. But you can see that from a cost perspective, they don't really change the game, right? They don't influence the decision. So either we're not